In the second part of our Bootstrap lecture, I would like to show one important variant of the non-parametric Bootstrap idea that I mentioned in the first lecture. In that lecture, I said that the underlying process which provides the connection between the past data and the future data is an IID process. Now, in many cases, as I have already mentioned there, the process is not an IID one like a time series data, or it could be like some Anova setup, some linear model setup. In those cases also, we can apply the bootstrapping idea. Now, I will talk about only the situation where we are in an Anova setup or in a linear model setup. The technique that I am going to describe is called Residual Bootstrap and is quite general. It may be used in situations other than just linear models, but linear model happens to be its greatest application area. So the idea is this, that suppose I have a linear model. I will write the general matrix form. I have a linear model Y. I write my vectors like this with an arrow. X, beta, plus epsilon. So this is a fixed part, the design matrix. Beta is the unknown parameter. And I have the assumption that this, typically assume that it is Gaussian, mean zero variance covariance matrix sigma square I. But I will not put that assumption. I will only say that these things are, so epsilon means epsilon 1 to epsilon n, and epsilon i's are IID from some distribution f. This is not the f distribution. I just said some distribution. I call it f. So maybe I will just erase this and say IID. Epsilon i's are IID. That's all that I have. And now I have, say, estimated something and I am interested in finding out, say, standard error or some behavior of beta hat. Then how do I do that? Had this been Gaussian, we know the standard theory, but this is not Gaussian. Now then the technique is, the idea of residual bootstrap is, you will again use the same thing, namely empirical cumulative distribution function, but the main power behind that theorem comes from Glivenko-Cantelli, and that requires that IID thing. So instead of drawing a resample from this Y, which are not IID, you draw the resample from whatever is given to be IID, namely the errors. The problem is, how can I draw a resample from the errors? Because I do not even know the errors. They are not observed. Y's are the observed data. X is fixed and known. So the technique behind residual bootstrap is, you first try to get a proxy for these things, the residuals, and then you resample them. So the way is this, you first find out beta hat, obtain in some reasonable way, some reasonable estimate. So bootstrap theory does not dictate that you have to use this square or anything, whatever seems to be reasonable, some reasonable estimate or some reasonable estimate of beta. Now using that, you find out epsilon I hats like this, or epsilon as a vector y minus x beta hat. Use them as a proxy for this. Now sometimes you are happy to do this, sometimes you might say you have done it using least squares and you feel uncomfortable because they do not all have the same variances. You might like to divide them by some estimate of the standard deviation to what is called studentize them. So you might either use them or you might studentize them. Studentized. And there are different ways of doing this. Studentized, some people call it standardized, and there's no unanimity about the notation. Some people will say if I divide it by its estimated standard deviation, I should call it studentized. If I divide it by its true standard deviation involving a parameter, I should call it standardized. Some other books say if you are dividing it by an estimate of standard deviation based on all the other observations, then you call it studentized. So there are all sorts of chaos. But the point is, you do whatever you want to do until you are happy with the assumption that all these things are, well, more or less IIT. Remember, it's an approximation. Entire Bootstrap theory is about approximation. So if you are happy with this, many people are just happy accepting this. Some people will do the studentization, standardization. Now they are approximately IIT. So what you do is you generate a resample from these. Same idea, simple random sample with replacement of the same size. SRS WR of size n. Same size. I give them a name. Suppose I call them epsilon 1 star, epsilon n hat star. Now we already had your beta hat. Add them back. So what you do is you had your x beta hat. With it you add these things, these resample things. Stars. Whatever you get, that is your resample fresh data. That is the thing that you use as your fresh data. So the idea is the randomness in y comes up because of randomness in epsilon. Epsilons are IID, so I applied the bootstrap technique to the epsilons and went back to the y. Same x, because x in any case is known, so we are using the same x. This is called residual bootstrap, and it's quite general. Whenever you have any statistical model where the randomness comes from some IID source, and most statistical models are like that, somewhere down there you have some IID random variables, then you do whatever you need to go to that low level, form some kind of a prediction of those residuals, of those IID things. They are called residuals in the context of linear model. Resample them and do the entire process backwards to get back to your data and treat that as your fresh data, and then carry out whatever we were doing earlier. So this idea is called residual bootstrap, less precise definitely than our usual bootstrap, but it is quite commonly used. Now let us quickly understand the steps of the algorithm. The first step that you do is you estimate the coefficients. Now after you have estimated the coefficients, you have to compute the residuals. Now I am always talking in terms of linear models. It could be some other thing. So estimating the coefficients may not be important, but coming to the residuals, that is important. So here by residuals I mean some kind of a prediction, reasonable prediction of the underlying IID component of your model. Now once you have done that, then you have to do resampling the residuals. This resampling is done exactly the way we have learned. You could use non-parametric bootstrap, you could even use parametric bootstrap. So you get that, and then you add back your resample residual to your fitted value, whatever you obtain based on your model, and to get your new data. So you recreate your data. Now that you have got your new data, you can apply to that data whatever method you have. So you apply that, your method to this data. So now all these three steps, all these three steps are to be repeated in that loop. And you just repeat them a large number of times, whatever you think meet. Remember, you are not repeating this step. You compute your residuals once and for all. Using those computed residuals, you are learning this loop. And at the end, you will do the same thing. You will track your performance and you do your aggregation there just as before. So the only extra step is you have to compute residuals and you have to recreate your data. So these are the things that are only two new things for residual bootstrap. I'm going to demonstrate residual bootstrap in the context of an analysis of variance model. So I have this data set of fake agricultural data. It has got a number of variables: variety, tilt, yield, and these are the various varieties: IR8, there is something called Joya, Taichung, and there are two types of tilts: plain and slope, plain, slope, and there are yields in some units. Here is just a data set to show a two-way Anova setup. I will first load this data. I will load this as dat equal to read.csv. I hope you all know that CSV is a very useful format, especially if your data contains missing value, which it doesn't in my case. So I first load it, and then I want to carry out a very simple linear model fit. I do not care whether the linear model is a good fit or not. This is not a lecture on linear model. So I will do fit equal to lm, my variable which is the response is yield, and I want to explain that in terms of variety and tilt. So just a simple additive model. My data set is called tat. So that's the formula object which says that I am trying to explain yield. Whatever comes before the tilde is the explanatory variable, is the response variable, and whatever comes after it are the explanatory variables. They are separated by plus. And this is the name of the file, tat. So let's just quickly do that. I have loaded it. It's always a good idea to do some sanity check that I have loaded the right thing. 30 cases, 3 columns. Let's take a look at the names. Indeed, they are variety, tilt, and yield. Now I do this fit. So I have done this fit, and I can take a look at my fitted model. It says various coefficients, etc., etc. Now what I need here is the residual. So I already compute the residual for me. So I will store the residual as res equal to fit $receipt. If you take a look at what are the things that are inside the variable fit, you can see it has got coefficients, residuals, that's the thing that I am using. And when I wrote receipt, it was just an abbreviation of residuals. And I will also need the fitted values. When I will add my resampled residual back to the fitted values, I will need them. So I will also say them fitted equal to fit $fitted. Fitted is an abbreviation for fitted dot values. Okay, I will execute them. So I have stored them. Now I will enter my bootstrap loop. For I in 1 to say 1000 this time, I am going to resample my residuals. So I'll call it temp. I'm not going to need them for long. So sample, I am sampling from the residual size, length of residual. Of course, I know in this case it is 30, but I am writing just length of residual, and then I have to say replace equal to true. That generates one resample thing. And then what I have to do is I will have to add it back. So my boot dat, let's call it boot dat, that will be your fitted value that you already have plus this temporary residual, and that is the thing. So this is your resampled quantity. So let's quickly do them without the loop. I will execute this line, execute this line. So I get my bootstrap data. So instead of my earlier y values, I am getting these values. Understand that these values are not actually same as the y values. I am not resampling from y values. You may have something here that never occurred inside your original y vector. So that is quite possible because I kept the fitted values as they were. I only resampled the residual. Okay, so now that I have done it, I might be interested in knowing what is the standard error of the interceptor. Say, just for the heck of it, how do I get the intercept term? That is easy. Fit $coef. That will give me the various things. The intercept term is this, which I can read as the first entry. So I will have to fit my model again. I will call it bootfit. Bootfit equal to lm. Same thing, whatever I have done earlier, I'll have to do once again. Let me just quickly see the fitted values. So I'll have to create my new data set. So I will do that in a second. Okay, let me create the new data set. So the entire thing with all the variety tilde, etc. So I will take my original data set, which was called TAT, and in TAT, the last column corresponded to my response. I'm going to replace that with boot TAT. So I will create my, so maybe I will call it boot Y, and then I will call it boot TAT as this. My boot TAT will be data dot frame. I will take whatever I had in the, except the last column, I remove that, and instead of that I will now use Y. I'm still calling it yield equal to whatever boot yield I had. Maybe I will call it boot yield. I'll call it boot yield. So I created my new data set. So let's just see how it behaves. So now I have got a boot TAT, names boot TAT. There again tilde yield and yield.1. No, I think I just goofed up. What was my original layout of TAT? Variety, sorry. I would have said -3. I have to remove the last column. Let's try how it was this time. Yes, variety tilde yield, but in the yield column, I now have my fake yields. And I will fit my same thing as I did earlier. I will call it bootfit. Bootfit is this, except that I will be working with my bootstrap data. I do not need everything here, I just need the intercept term. So I will store it. Say I will call it intercept I equal to bootfit $quef1. So I'm saving it, so I have to just allocate the memory. In fact, you can avoid allocating the memory. Well, I'll show you another way, which is less efficient. You start with the empty list. That's an empty vector, and you can write this C intercept this. That will also do. In that case, it is growing. So as a result, it will be allocating memory again and again every time it runs out of memory. So it is slightly slower, but it is easier to type. And even if you change this number to something else, this is just going to work. So at the end, you will have INTCFT, and you can find out its standard error. You wanted to find out the standard error of the intercept term when normality assumption is a suspect set. So in fact, from our Gauss-Markov theory, we really do not need normality assumption for second order moments, but you can find whatever you want based on that. I might as well find a confidence interval that will not be given by just Gauss-Markov thing, and I will say probabilities are 95% confidence interval, so 90% confidence interval 0.5 to 0.95. Okay, so I will just execute it inside the loop. Good, no error. And I get my 90% confidence interval for the intercept term without making any assumption on the error vectors other than the fact that they are IID. So my original data set, the yields are not of course IID, but those epsilons were IID, and based on that I obtain my 90% confidence interval. So basically that concludes our entire discussion on Bootstrap. There are certain other things that I have not mentioned. Number one, there is a package in R called boot, which will perform this loop inside, but I personally do not like using that because that function itself has its own syntactic idiosyncrasies. You will need some time to understand those things. And anyway, you just write a simple loop, and when you write your own loop, it is far more versatile. And the time that you spend in understanding how to write a loop in R is well spent because loops are useful in other places in R also, whereas the boot package has its idiosyncrasies. It is very specific to that package only. Any time you spend understanding that will not be useful in any other place in R. So that is one thing, but you might try the boot package. And if you want to get a tutorial on that boot package, you might try the R News, that is the online journal, R News. It is in December 2002. The first article, December 2002, R News, that has a nice introduction, tutorial type introduction. Now the second thing that I did not mention is about how to perform Bootstrap for a time series model. This residual Bootstrap may still be used because many time series models are actually given in terms of some IID error like moving average methods or autoregressive methods. So you can estimate the residuals, resample and add them back. However, there people like to use something else which is called block bootstrap. So you have the entire time series, you chop it up into blocks, and instead of reshuffling or taking a simple random sample of the individual numbers, you reshuffle all those, or you take a resample of those blocks. Since you take them to be large chunks, so the temporal dependence remains more or less unaffected except at the boundary of two chunks. The theory is much more involved, and personally I do not think that they perform as great as ordinary non-parametric bootstrap or even residual bootstrap. So that's basically all that I wanted to talk about Bootstrap theory.